you're awake after lunch. If you attended yesterday's IoT hackathon in the evening, you might have seen some of the things that you can do with Reactive. Frank is the co-founder of Reactive, and he's going to tell us all about how you can build OSGi bundles block by block. So, okay.
Thank you. I'll do my very best regarding the sleeping. So hi everyone. Now I tried to do the impossible because I wanted to explain to myself and to you OSGi in two pictures. Why are we using OSGi? And that's the first picture. That's your application and also my application without OSGi. That's not meant as an insult. We all know how things happen. You start easy and things get more complicated and intertwined. So what you end up with is a mess, basically, that you would like to throw away. Okay, that was the first picture. The second picture with OSGi is this one. Okay, much better already. So you see, we have the same stuff. We just put some boxes around it. And of course, in OSGi, these boxes are the bundles. Now the question is, this nice modularity gives us the possibility to easier understand our application. It is structured easier, so we can exchange parts of the application. It's easier to reuse parts from others. So on that level, it's very good. But in this talk, I would like to look inside the OSGi bundles and look what can we do there to have a good structure and make good applications. And before I delve into that, I would like to tell you which kind of systems we are actually looking at, because we have some type of system that we are looking at. And you see the G in OSGi, which is standing actually for gateways, at least formally, is coming back because it gets a lot of attention in the IoT space. We have IoT application gateways. Now, what do I mean by that? These are gateways, for instance, roadside stations that could monitor traffic that is driving through, but also onboard units, for example, on a truck, monitoring the load or temperature of things that you have loaded or where it is. And then there's, of course, all those residential gateways that already run OSGi, perfect examples. And there's lots of stuff more. Because it's after the lunch and because everybody likes pictures, I have some pictures actually. It takes some time, there's some delay here. This is one example where gateways could be very interesting. It's a parking house. I parked there some months ago for the first time. I never saw such a system. You see here, they have sensors which of the parking lots are actually empty. So it lights up green or red if the car is standing there. And you have a guiding system that tells you in which direction you should drive, so you find the last space. And then also an example directly outside of our office. Here, the community is counting the number of bicyclists that are driving through. Now you see here that's three cyclists per day. That's not the real number, but the shutter time of the camera was so short that it didn't get all the digits, so it was more than 300 on that day. And right beside there, you have another gateway application where you can actually rent bicycles. So these are just some of the typical use cases of these gateways. And there a lot has happened, a lot of nice things has happened during the last years. That is all the gateways that I usually have on my desk. Now you know how unorganized my desk must be, so I put them out. That's a ReliaGate from Eurotech, Sierra Wireless, CloudGate. This one is from Contron. That's from Intel. We have a Raspberry Pi, of course, and some hardware from Freescale. That's just examples. All of those run Linux and Java and OSGi. Very nice. So that's a big arena where we can actually build applications. Okay, back to the IoT application gateways. What's their property? Now, in contrast to other applications like enterprise applications, they work pretty much autonomously outside, like in the parking house, right? There's no human being there and supervising them all the time. And that also means that we have to have them remotely managed. And they have an interface to other things. That means real hardware or things that people don't see as a typical computer interface. And that's important because that means these gateways must be reactive. They must be responsive and react on these events often within a short time. And of course, they are all connected via network. So we have also to pay attention on what the network does, because it could go away for some time. Now back to OSGi. How do these applications then look like? And I have some easy picture. Here you see I make the simplification that I have a main application bundle here just for the sake of the argument. It could also be more complex than that. But usually you have one such main bundle that encapsulates your application, and it consumes services from other bundles. And these other bundles, here just some examples, they could contribute control of the general purpose I/O. The runtime is very important because that's the source of events, as we will see later. A communication protocol like MQTT or a field bus protocol like Modbus for communicating with hardware, and maybe a database, right? So these are typical bundles that you would use in your main application bundle. Now let's talk about events, and you see we are approaching the problem because what is the source of events that our applications have now to take into account? So the first is lifecycle. So because it's a managed application, our application has to adhere to the OSGi lifecycle. So we have to start it, that's easy, but we also have to listen if the OSGi container would like to terminate our application. So we have events there. Then there are also other bundles that I have shown, and because of the dynamic nature of OSGi, these other bundles may create events that we have to react to. They may vanish, for instance, or they can be updated, modified in some way. So we have to listen to these events too. And then, of course, because it's remotely monitored and we can change the configuration of our application, we have to react to configuration changes. And sometimes that's easy because we just have to update some data, right? But in some cases, we would like to react and we would like to introduce some behavior. Easiest example is you would like to connect to another MQTT broker and you just push a new address. So what do? You have to turn down the old network connection, and then you have to reconnect to the new broker. That takes some time. So it's not only updating data. And then, of course, because it's a networked application and it communicates with other system parts, we have to react on messages. And again, the network is a source of events because the network can fall down and it can come up again. And we have also to handle hardware. So many sources of events. And that also means this is an exquisite problem of concurrency. So that's what makes these applications very, very hard. I found one very good tweet about concurrency. I just show it to you. I'm not going to read it. It's a very nice one because it really tells you what the problem with concurrency is. Also that we might not be so aware of that problem in the first place. Now I'm showing you an example why. Okay, back to OSGi. We have our decomposed system, here these bundles. What's happening inside our application bundle? Well, what should happen there? OSGi doesn't address specifically the problem of concurrency, and that's okay, so it doesn't give us any constraints. We are basically on our own and can use all the mechanisms that we have in Java. The only thing is that we have to do, well, we have to put the application inside the start method that gives us the bundle context. So we have to adhere to the lifecycle of OSGi, and then we can do whatever we want. So where's the problem? Because we have Java threads, we have synchronizations, we have Java util concurrency, for instance. Okay, what's happening? That's a programmer, and we need to do, let's say, two things at the same time. Well, that's easy, okay? So we have threads, cool. Here we have a pink thread and a blue thread, so we can do two things in parallel, no problem at all. Now, it turns out that there's some dependency in the data, right? So we would like to synchronize data between these threads. So what's happening then? We still can do this. We have synchronization statements. We could also use semaphores. which are a bit easier to use. And with 2 threads, you will manage. But then we get a new feature request, right? Our application gateway should do some more stuff, and we find there are some dependencies. Like, for instance, we're updating the configuration, and then we find out, okay, in that case, we must pay attention on something else. So we are getting another thread, and you see our developer now starts getting to get a sort of a headache. And at a certain point, no, let's just add another thread. It just gets so ugly that you would like to throw everything away. And that's the problem, right? So it starts very easy, but as soon as it gets too complicated, it's actually too late, because now you're a prisoner in your own code. And you don't want to throw it away because there's so much things working with it, but you cannot really continue with it either. So basically you have this mess. I tried to symbolize this here. You really have spaghetti code. But that's not spaghetti code in the old sense of spaghetti code, because it's unstructured. So everything is nicely structured in methods and interfaces and if statements and so on. That's not the problem. The spaghetti comes from the concurrency. You don't know in which thread things are happening and how they synchronize with each other. And that's much, much more difficult. So more than once, I had to dive into a framework, an implementation of such an IoT gateway that was just programmed the normal way. The data part is usually easy to understand. You get a feeling for that. But you have to have an enormous overview of the entire application in order to understand how the synchronization works. Okay, so what can we do about it? The answer that we found is graphics. So we can present the entire application by means of graphical building blocks. And now my reaction as a programmer would be, why? I'm a programmer, so I want to program and I want to code. If I would like to paint, I would be a painter, so I don't want to do that. If that is your opinion, and I say, well, we agree on that. And that's also why we're using the graphics in a very, very smart way. So I'm going to show that to you now, because we start actually with Java operations or methods. Let's say we have a method here that switches on an LED. There's nothing wrong with the code to switch on the LED. Let's say we have here code from the Pi4j project. That's how you switch on a LED. Of course, something is happening with drivers and so on in the background. Perfect. So you have this operation switching on a LED. You have a similar operation to switching it off again, right? And we can graphically represent them with these elements here. Now we would like to blink an LED. So what do we have to do? We have to add a delay in between. Now, it's no problem of adding a delay in between two methods in Java. It's just very ugly, right? You have to pause the thread and you have to catch some exceptions that most of the people don't understand, including me. And it's not very nice. Graphically, we can do it differently. Well, we just put this timer in between. It's a nice symbol. And we can generate the code that we need very efficiently, automatically. But the thing that we care about, namely switching on the LED and switching it off, so that's part of our application, this code we write. The one for delaying the action in between, we really don't want to write. There's no honor and nothing special in that code, apart from that we just often do it wrong. Okay, so these are two operations, and we have already here an interesting behavior that might be reusable because it's blinking an LED. So what can we do? We can encapsulate it in a building block. So we just draw a box around it. Right? Now we have a building block that can blink an LED. From the outside it looks like this. Here the LED goes on and it tells us automatically when it goes off. So we get an event that is called off. Very nicely. Now let's take this one step further. Let's make an LED that blinks periodically. So how do we do that? We add this network here. So we have a timer here. And you see when we start this, we start the timer. Once the timer expires, it starts the LED, so it blinks. But it also restarts itself. So we have a periodic timer actually here. Now a periodic timer, perfect candidate for another building block. We also encapsulate this one as a standard library element. And from the outside, then it looks like this. So we have a periodic timer. We can parameterize it. And every time it ticks, we get an event here, which can then trigger whatever we would like to have. And now you understand the game. We have now created 2 building blocks already. Let's make a third one, because now we have a periodically blinking LED. Could be useful for a lot of stuff. So we make a building block out of this again. So we have building block and building block and building block. In case you're concerned, there's a processor, a compiler, that takes all these graphics away. In the end, there's just the code that we need, and exactly that code. So you can wrap 50 things into building blocks. All of that goes away during code generation. So this is just a design time concept. Okay, what else can we do apart from triggering things by timers and making building blocks? We can join data, for instance. So if you write that a method depends on 2 parameters, then this is implicitly implying a join. So it will not execute this procedure before all data has come. So immediately when the second data type arrives here, we will call the method, and then we will compute its output. And then there is also a very nice feature with buffering. Now here you see a bit more complicated composition of building blocks. What is this doing? It gets in some data type. Here it's a location event from some application that we would like to send. We put it into a JSON serializer so that we make a string out of it. We then create an MQTT message. So we're putting a topic on it and a quality of service. And then we are using this for sending it via a specific building block for publishing MQTT messages over there. Since publishing could fail, we're putting a timeout here. So that means that processing this event will eventually create a confirmation, right? Eventually, it takes time. And that's a problem, because it takes some time, and we are getting many events that we would like to send. We need to buffer, okay? We just add a specific building block that adds buffering. Now you might ask, well, the buffer, it could be a Java normal data structure like a list or a set. And in fact, there is a list or a set in this buffer. However, what we also get is the event when it can actually continue to process the next event, right? So it's an event-driven buffer. And this you can easily use for decoupling these events. Another example for a building block to coordinate concurrency is here the limiter. That is a building block that, let's say, we have here a source of data, and we are not sure how often this data is coming, and when we want to curb the number of messages that we are actually sending over a bus, we could just add a limiter here that throws away more than X messages per second, for instance. So a very easy building block that you can just add into the stream. Okay, so that's what we are doing regarding concurrency. Now, how is all of this working together? You see, this just develops into a library of building blocks. Very nice building blocks that we can use for useful stuff. It's like the building blocks from Lego that you might have used. These are small building blocks, so they are smaller than OSGi bundles because they are used to build the OSGi bundles. The OSGi bundles, in a way, are the big building blocks for your system. These are the small building blocks for your application, right? And there could be building blocks for Modbus, for JSON, for MQTT, for buffering, and a lot of more. And then you arrange them and combine them to applications. The applications, as you have seen, they are then represented by a hierarchy of building blocks. So on top, it looks very simple, and then it goes down into building block and building block and building block until you get elementary building blocks that only contain Java operations. And all the time, whenever you need to write some code, you put it directly into the building block and you write your operations, exactly that code that is important. And then we generate an OSGi bundle out of all of this via code generation, very advanced process, but I'm not losing too many details about this. And then we can deploy this on the gateways. Okay. Now back to OSGi and concurrency. So far, this is general for Java. What does it have to do with OSGi? Two things. The first is that OSGi heavily uses Java interfaces, and that's very interesting because that's the way modularity works. That's the way we define interfaces between the modules, obviously. And modularity has to do even more with concurrency, because the way OSGi is organizing modularity leads to new events on its own. So let's have a look first at the Java interfaces. Java interfaces, like many programming interfaces, they document the names of methods and the types. So the input types and the output types, you know that. So that's very good. But with regard to event-driven systems, what is missing is actually the sequence in which we are allowed to use the operations. Right? For instance, you have a Java socket, right? Now, most programmers know by instinct that you have to open the socket before you can actually do something with it, and that you have to close it in the end. But that is really something that you only know if you have used it before. And that's also why you say that you get familiar with an API, because you know all these hidden dependencies that you have to use. So sequences are not formally part of the Java interface. In addition, there's timing. And what do I mean by that? Well, it's how much time a method needs, if it is blocking or not. That's very important information, because if it's blocking and you're calling it as if it wouldn't block, well, then your application is blocking. It cannot process anything else. And that's a big problem if your application should do at the same time some other duties on another interface, so it just cannot respond in time. Now, the question that you would ask here is, of course, why don't you read the documentation? Because there you will read that you have to open a socket before you can do anything with it. And you could also read that a certain operation is blocking, right? Now, number one, it must stand in the documentation. So, and I'm thinking good APIs, they write it down, but your colleagues and yourself, you probably don't write it down, right? But a much bigger argument is that the compiler doesn't read Javadoc. So the compiler cannot tell you, well, you're blocking your application here, because it doesn't know that. So you won't get warnings, and that's what we would like to get, right? When we use the tool, we want that the tool does the hard stuff for us. So that's why we would like to have that as a part of the API. How do we do that? Let's go back to our building block that we have created, the one that blinks, the LED, and we just add a contract to it. And the contract now for this one is pretty simple. You see here, we have actually a state machine diagram. It has an initial state where it starts, then we switch on the LED, then we are in state active, and then we see in the next system step, so that means not immediately, the LED will switch off on its own. And that means if we are switching on the LED, we can do something concurrently. We shouldn't wait for that, because it will happen sometime in the future. Right? And in that way, we can give out the information which methods are actually blocking and which you can evoke within the same run to completion step when you execute the system. Okay, that's an easy example. I have one that is a bit more evolved. Here, that is a real case that happened not too long ago. Maybe I should explain to you. I wanted to make a building block that creates a request-response pattern via MQTT. Now, you know MQTT is usually communicating with a publish-subscribe pattern. But let's assume that because you have an MQTT broker running anyways, and you would like to implement a request-response pattern, you would like to use MQTT for that. So I created this building block. I will explain to you in a minute how it works, and I was very confident that this is the first and the good solution, because it must obviously be right. It looks very good. This is the ESM, or the contract of the MQTT building block. So you see, not going into details here, but there's a little bit more going on than just with our blinking LED. It has some states where it's active and where we can actually publish messages and where we have to be prepared to receive messages. And I was very confident, again, that this is the proper solution, because I have done this before. And I start the analysis and I get this one. Well, you terminate this building block, but you leave MQTT open. Okay. Now, maybe I should look into it and find out why this is happening. And now we have the benefit of the contracts, because now the analysis tool can automatically show to us what's wrong. And this is happening here. So we are initializing the MQTT building block with some configuration data. right? Here we are calling a Java operation. What could happen now is that it actually fails initializing, maybe because the network is down. That would be one alternative. But now let's assume that it says, I'm okay. Then we are making a technical break here. After that, we are actually creating a request message. And we are pushing this message out in order to send it. So far, it's good. But now we are eventually receiving the answer. And we are very, very quick here because we are already going out of our MQTT request block. We are not actually switching off the MQTT connection. Now you could argue if you actually should do it or if it should persist, but in this case, as we formulate this building block, it's wrong. So the solution would be then to switch it off, wait for that, and then give out the response. Then the behavior would be consistent, right? Again, this is just an example. There are other cases where these kind of race conditions are very severe. Also deadlocks, we are able to find them. What I should note is that these are kind of mistakes that are difficult to find by testing because testing is only as good as the test cases as you write. So you would only detect this if you would explicitly make a test case that would catch this interaction. Okay, the other point was the OSGi events that have a dependency between concurrency and OSGi. And I told you that OSGi in itself, by managing modularity, creates events that can interfere with the events of our application. And what can we do with that? Well, we can create building blocks for OSGi. So the framework itself gets represented by special building blocks. Here are the building blocks that we have built for OSGi. So we have a building block for terminating an application. We have a building block for listening to configuration changes. We have event handlers, and we have service trackers. Now I'd like to show you some of them. Here we have the event admin service. You know, this is a mechanism that comes with OSGi where one application bundle can communicate either internally via events or with other bundles that run on the same instance. And we made a building block to send an event asynchronously. So you start it here, then it gets the event admin service, and you can post an event. It also tells you when it's ready, for instance. And vice versa on the receiving side. Then you can use a building block where you can subscribe to a certain type of events that you put in here. And then when it's ready, it will receive these events for you. And you can use this for triggering, for example, the LED to blink or whatever else, whichever other building block you would like to use. Here we have a building block for a service tracker. And with that service tracker, you specify as a parameter which kind of service you would like to have. You start it, and then you get notified as soon as a service of that type is registered, as soon as it's unregistered, or when it's modified. And you can react on these events appropriately, not only by setting the data, but also by triggering more actions. Now at that point, you could say, well, I'm using frameworks, component frameworks that manage these dependencies for me. And that's very nice. But in some cases, and particularly for IoT application gateways, you would like to manage these service discovery mechanisms probably on your own. You wouldn't like that your application doesn't even start up just because a service dependency cannot be satisfied. Then you would like that your application starts, but it would trigger some behavior because there's a timeout, it doesn't find the database, for instance. But at least you could do something about it. So this is something that you would like to handle in your application. That's why we make a building block for it. Here's a similar building block for the termination. That's actually very easy. So you start it in the beginning, and here you will get notified that the bundle would like to stop. I will show you in a minute why this is a benefit. Last but not least, here, a building block for configuring the application. And here we're using the Eclipse IoT Cura project that uses the config service in OSGi. So let's say we have here an application and we would like to listen to configuration changes. Well, what we do is we describe these parameters in the meta type specification. But just by using this building block, the config listener, we actually make this bundle that we will generate configurable remotely via the Cura web admin. It would work easily also for for the other frameworks that have support for configuration. Okay, now why are these building blocks a benefit for me? I made a very simple demo application here. It's called Hello Cura. So we start our bundle and we print out hello, nothing special with that. And we start to listen for the termination. In that case, we generate a string that is goodbye, and we're using speech synthesis for let the computer speak this. Okay, that's very nice. I'm using the speech example always because that's an operation that takes time. We have another building block that listens to configuration changes. When we do that, we are also generating some speech. And that looks perfectly fine. So whenever we change the configuration, we not only update the data, but we are also starting some event. Again, I felt very confident when I was doing this, and I was again surprised that I got the message, well, that doesn't really work because, well, I'm starting my termination sequence here because I'm stopping the bundle. I'm doing the goodbye stuff. I'm letting the computer speak goodbye, and then I'm really terminating the system here. However, what I forgot, in the meantime, a configuration change still occurred, right? These are unrelated events. Somebody changed the configuration, and I stopped the bundle. So what was happening, I was doing this termination while I was in the process of speaking another text. And this is just a representative example for using a resource, and it should be used and terminated the right way, right? For instance, that you close the sockets, that you flush some I/O and so on. So here, because of these contracts, because of these building blocks that manage concurrency, the analysis actually found the mistake and told me, well, you should terminate that properly. Now, the proper solution in this case, in case you're wondering how we should do that, was by using, for instance, the buffer. That's just one example. So here we would create that string that we would like to speak when we change the configuration, and we put it into a buffer because speaking is something that takes time and we can only speak one message at a time. The same with the termination. So it just is added to the buffer. And now we have a perfect kind of guard for when we can terminate correctly. What's happening if we terminate, we are stopping the buffer, and the buffer is so smart, if we just stop it, then it will tell us, well, I still have stuff to do, let me do that. And after it then spoke all the text that we have, one after each other, it will finally go into stop. Okay? Do we have time for a little demo? Yeah. I have programmed this actually.
3 more minutes.
Okay, perfect. Now let's see. So this is the application in Eclipse, and I just want to start it. Let's see. I have started it previously here, and now I see. I stopped it previously, so there wasn't. So you see now the bundle that I created is resolved, and it has the ID 24. So I think I started. Okay, now it said hello to me. And if I now refresh the web console, there is the application. Now I have some data, some configuration data that I would like to adjust. And let's just change this value here. And now I can apply this. Are you sure that you would like to update the confirmation? Yes. Oops, something is wrong with the audio. No, usually it should have been talking. Okay, classical demo effect. Let's see. Stop 24.
Goodbye.
Whoa, okay. So the audio was working. So what you have seen since the goodbye, it took some time. It first told us goodbye, and then it terminated the bundle nicely, right? So that was because of the buffer. Again, it's a very, very simple application that you can hopefully grasp in some minutes. So that's what we have achieved with this simple bundle. Obviously, you can create more complex application. With that, we have at our booth a lot of examples that you can look at if you're more interested. We also have, so first of all, I hope you like this. And these are the next steps that you can take. Visit our websites. We have really cool tutorials. So we have put a lot of energy in that it takes only a short time to get actually started. So most people get something running after half an hour, some demo systems and tutorials that you can start with. We also have the IoT playground, and there you can build an application with the Raspberry Pi using MQTT and Co-op and the camera, so to make an IoT application. And of course the tutorials that I mentioned. Okay.
Any questions? We can have a couple of quick questions. No questions? Well, thank you so much. That certainly kept me awake.
Thank you.
Would it be possible for you to give me your PDF so we can put it on the website?
Yeah. Yeah.
Do you want to copy on here
Okay.
or email me whatever you prefer?
I would email you.
Email me?
Yeah.
Okay.
Because I want to compress it.
Okay. Is it what are you
Ich kann den Talk danach wieder zurechtschneiden. Also ich mache den Zentrum hinten was anderes, weil ich muss machen. Das ist halt ein bisschen mehr suchen über...
Alles klar.
Okay. I got it.
So I can compress it until...
Yeah, here. I'll give you my card. Thank you so much. That was quite interesting. Where are you located? I'm in Portland. Hi, the next speaker. Hi, how are you? Good to see you. We met last year. Hi.
Fused files of mine, so...
So you both going to talk?
Yeah, we switch in between.
Okay.
Start.
Yeah. Have you guys considered joining OSGi?
German or English?
I start, so...
We could also put it on the table. It's pretty good. It should be
that's
fine.
perfect.
Or maybe, do you have one laptop? Or okay, habt ihr ein oder zwei Laptops? Okay, was man auch machen kann, ist es irgendwie, irgendwie dran zu hängen an den Laptop, sodass es so ein bisschen zu euch gerichtet ist. Wenn es okay ist.
Wir können du kannst erstmal ummachen und dann
Also auf dem Tisch ist auch okay. Auf dem Tisch ist auch okay.
aber wenn es so geht.
Wie es euch lieber ist.
Dann müssen wir nicht mehr wechseln zwischen.
Ja. Also wir haben es letztes Jahr auch so gemacht teilweise und es hat super funktioniert. Wenn ihr wollt, ihr könnt es auch tauschen. Ist euch überlassen.
Ich mach's dran und er kann es ja dann abmachen. Ich möchte es ja dann hinten noch in den Saal laufen.
Ja, klar, wenn man so hin und her läuft, dann ist es besser, es dabei zu haben. Aber ich lege es euch einfach mal hin und ihr könnt es dann machen, wie ihr wollt.
Actually, interesting. It kind of came in my mind when I was working in an Italian company.
Ja, das funktioniert auf jeden Fall.
Let's say.
Und ansonsten einfach die andere Geschichte, die kennt ihr schon mit VGA-Kabel und so.
Tool for actually being able to write your printed networks, because you know printed networks. It's very similar to your approach. Basically, artifacts. The tool was called artifacts.
Do you want me to
Was one of the, let's say, the few available all over the world, and actually we're modeling protocols with the printed network. And when I say this, actually it's very similar. Actually, more improved because now we have blocks. Kind of very good.
We started first with state machines.
Yes.
Right? But then I found out that if you compose things concurrently at the same time, it's much easier with using activity diagrams with the PatriNet semantics.
Yeah, that's something.
But we couldn't use pure PatriNets because it was difficult to catch tokens that are somewhere, but the activity diagrams, they allow that you stop the timer or other things. So that's
No, actually, we kind of we expanded the methods to other type. And basically, it was very easy, as you said, to develop, say, a